I have to reopen all the tutorials from urinary system come down. Okay. I will open as well tutorials for the other things, and I will leave them open until the end of the semester. As long as you submit them for the end of the semester, I'll still accept them. And the end of semester, of course, means end of week 13. All right. So that's the week of the in-course test. That said, more likely than not, I'll be using tutorial time to lecture. Okay. Because we need to try to best to make sure we finish the syllabus. When did you send that email, Chevelle? I haven't seen that email from you. All right, Chevelle, if you're hearing me, try resend me the email today, so it'll be on the top, because honestly I haven't seen it. Right? Generally speaking, if you send me an email and you get no response from me in a week, it means I'm not seeing it. Right? I don't normally just look at the things and ignore them. Okay, so that said, remember, if there are any issues you need to deal with, do try to send me an email this week. The earlier the better, so I can start working on it. Right? We don't have a lot of time. I know there are 1 or 2 people who had an issue with in-course test 1. Please email me about it, because we need to get that dealt with. Okay? ASAP. All right.
So,
Go ahead.
last question. For the integumentary skin write-up with the references, well, integumentary system write-up, do we need in-text citation or just the
No, you don't
reference
need in-text
page
citation.
at there? Okay.
It would be nice though, but I mean, if you can, great. But I'm not gonna kill you over it. It would be nice though.
Excuse me, sir. I have a question.
Yes.
I heard you said that there will be no labs for this week. Does that go
No,
for...
no, no. I said that you'll be completing the electrolytes worksheet.
Okay, and that goes for Mrs. Thomas's class as well?
Yes, I spoke to her already.
Okay, thank you.
Okay. But remember, next week we're supposed to see in the lab, right? All right, electrolytes. So what I'll probably end up doing is taking some of the tutorial time today, because as I said, we need to finish up. We need to do the digestive system, or at least start the digestive system today. And next week, then of course, I will do the same thing where I'll take the class and a portion of the tutorial time. So fundamentally, functionally, I'm teaching the tutorial time. We don't have the time for the tutorials. That said, in week 13, I am hoping to be able to take, even if it's just 1 or 2 of the tutorial classes, and run through the answers, even if it's just to do it after your in-course test 2 in week 13, right? So yes, I'm still going to go through them. Okay. Okay, fluid electrolytes for like the 5th time. Now, your body basically stores fluid in 2 ways. Okay. We have what is called an intracellular compartment, and another one which is referred to as an extracellular compartment. Now, nurses in particular, fluid and electrolytes are very important. Okay. Of course, pharmacists as well, because you will be giving medication to help to balance problems in these 2 compartments. But nurses in particular, you must know this stuff, because it's going to come back up later on, right? So you have the intracellular fluid compartment and the extracellular fluid compartment. No surprise, your intracellular fluid compartment is inside the cells, because of course, as you know, intra means inside, right? So if you take all the fluid inside your cells, that is your intracellular fluid, okay? Then now you look at the fluid that is outside of the cells. So we're talking about fluid in the blood, fluid in the, so that's plasma, okay? We have fluid in the interstitial spaces. That's the spaces between the tissue, so that's tissue fluid. Of course, you're looking at fluid in the lymphatic system as well. All of this would be extracellular fluid. Fluid even in the synovium, Remember, synovial cavities have fluid in them. The surfactant that you find in the lungs, all of this stuff will be considered extracellular fluid. Okay. Now it mentions here intracellular fluid. About 40% of your body weight is intracellular fluid, and 20% of your body weight is extracellular fluid. So simply put, most of the fluid you have is stored inside your cells. Okay. So this is a simple graphical representation of as I mentioned, the relative size of the body fluids compartment, right? So it shows you intracellular fluid, roughly about 67%, extracellular fluid, roughly about 26% of the total, right? And it even mentions down at the bottom here, for the extracellular fluid, it divides it into interstitial fluid at 26%, plasma at 7%, and cerebrospinal fluid at about 1%. So 7 plus 1, that's 8. 26 plus 8 is 34. But, well, I guess so it adds up to roughly 100%. It's 101% because it should be 66, but still, everything adds up to roughly 100%, right? Now, osmolality, osmolarity, what are we talking about? It mentions here is the number of dissolved particles or solutes in 1 liter of water, okay? So the number of particles in 1 liter of water refers to its osmolality, right? Now, sodium, your good old Na plus, is the most important electrolyte of the extracellular fluid, right? So, as it says here, sodium is the greatest contributor to osmolality because of that. Remember when you were doing AMP1, when you were doing things like nervous system, they mentioned that cells pump sodium out and potassium in. That was not just for nerve cells. All cells do this. Okay? So you have plenty of sodium in the tissue fluid. And this, of course, is what affects the osmolality, or if we say colloquially, the concentration of the tissue fluid, right? The more sodium you have, the higher the osmolality, therefore the higher the concentration of the fluid, okay? Now, why is concentration important? Because, of course, we know this of the fusion gradients, right? Moving things from high to low requires a difference in concentration between high areas and low areas, right? So sodium and other electrolytes are going to help with this osmotic balance, okay? Now, I'm assuming everybody remembers osmosis versus diffusion, okay? Diffusion, as you know, is simply the movement of molecules from an area of high concentration to an area of lower concentration. That's all it is. It doesn't have to be what it doesn't have to be anything in particular. As long as it's moving from high to low, that's diffusion. Okay. Now diffusion has different forms. It has more specialized forms. For example, facilitated diffusion, where things are going from high to low, but they must travel through a protein of some sort, right? So this for example, is a gated channel protein. So this could be a sodium channel, for example, right? Or they could use carrier proteins, as I'm sure you did in EMP1. So facilitated diffusion, high to low, same way, but they're traveling through or they're assisted by some sort of a protein. Whether it's a channel protein or a carrier protein, it needs help. Okay? But once again, they're simply different forms of diffusion, which means no energy input required. Then, of course, we have osmosis. And we'll talk about osmosis in a little bit because osmosis is a further specialized form of diffusion, right? That said, let's talk about tonicity. Tonicity is important for all types of diffusion in order to cause the movement of substances, okay? Now, you would have done this at CSEC, so I'm sure this will all sound very familiar to you. Tonicity, the ability of a solution to cause a change in water movement across a membrane. Basically, this is what tonicity is measuring, is how proteins or substances in water in one fluid compartment affect the movement of water into or out of that fluid compartment, right? So basically, a cell is a fluid compartment, okay? And the concentration of substances inside this cell is what determines whether or not water flows into the cell or water flows out of the cell. That is tonicity, okay? Which means, of course, you're always comparing your compartment, where you have your cell normally, is your compartment, to the external environment and seeing how water is moving relative to that internal environment or the cell, okay? And we'll talk about the importance of IV fluids and this in a little bit, right? Now, here are some terms you would have come across already. So tonicity breaks down basically into three types. You have isotonic, hypertonic, and hypotonic. Okay? Isotonic means that the concentration of the solution that your cell, remember now when we talk about compartments, we normally refer to cells. Okay? So in isotonic solution, the relative concentration of water inside and outside the cell is approximately the same. So they have the similar osmolality. Now, when they have similar or the same osmolality, it doesn't mean that water doesn't move in or out of the cell. What we get instead is something called dynamic equilibrium. It simply put means because the osmolality inside the cell and outside the cell are the same, so that's why it makes them isotonic, you're gaining and losing the same amount of water, therefore there's no net change in the volume of the cell, okay? For the most part, in your body, you want an isotonic situation, okay? You don't want your cells to be overly gaining or losing anything. So isotonicity is closer to a homeostatic balance. Now, if your cell happens to be in an environment with a greater osmolality outside than inside, this normally means you have more sodium outside in the fluid outside relative to fluid inside. You're setting up a situation of hypertonicity. And of course, hyper as in hyperactive, hyper speed, whatever it just means more. Okay. So when your solution is hypertonic, it is more concentrated than inside the cell. Okay. And because of that, and as we know, this means the concentration of water inside the cell is higher than the concentration of water in the fluid around the cell. Of course, water moves from high to low. Therefore, water will leave the cell and go into the environment the cell is in. This, of course, causes the cell to shrink. okay, shrivels away. If it's a plant cell, you get plasmolysis. So the cell membrane pulls away from the cell wall, and it's easy to see the cell membrane, okay? In the case now where the osmotic concentration inside your cell is now higher than the surrounding environment, or the osmotic concentration in the surrounding environment is lower than that inside the cell, basically the same thing. What happens, of course, is that it means that your water concentration relative to the solutes is higher outside the cell than inside the cell. And of course, once again, water goes from high to low. So water from outside will rush into the cell, okay? As you can see here. Now, if the concentration gradient, if the osmotic concentration difference between inside the cell and outside the cell is great enough, then water will continue to flow into the cell. And if it's an animal cell, it will simply swell up the animal cell until eventually the membrane ruptures, cell dies. That, of course, is lysis. So you have lysed the cell, okay? Plant cells, of course, cell walls mean plant cells will not become lysed, but they will become turgid, okay? All right, so that was a nice CSEC revision, right? Osmosis. Now, people always remember osmosis. Simply put, osmosis is the movement of water from an area of high concentration to an area of low concentration across a selectively or semi-permeable membrane. Now note, I have said semi-permeable and selectively permeable differently. In CSEC, you all have a tendency to be told that they're pretty much the same thing. You all tend to use them interchangeably, which is not your fault, of course, because that's what your teachers tell you, right? But they're not the same thing. A semi-permanent membrane, by the physical nature of the membrane, tends to allow substances of a particular size or charge through based on small pores or that may be present in the substance in the membrane, or charged molecules that make up the membrane. Okay, so we can manufacture semi-permeable membranes. So for example, in reverse osmosis, when you're taking seawater, for example, and you want to extract drinkable water out of it, you use reverse osmosis. You have actual membranes that you're pumping seawater through. And the membranes allow for the movement of H2O through, but charged particles like sodium and chloride are rejected by the membrane. Those are semi-permeable membranes, okay? So what's the difference with selectively? A selectively permeable membrane is a biological membrane with purpose-built proteins, which can allow for the changing of the permeability of the membrane. The membrane you have in the reverse osmosis plants, they have a set permeability. There's not much you can do with them, right? But your cell membrane can increase or decrease permeability. So for example, there are sodium channels, as you know, in your cell membrane. If your cell needs more sodium in, can open those sodium channels to allow sodium to flow in. If there's too much potassium in, it can open potassium channels to let the potassium out. It can choose to do this. So it can select what it wants to do, hence selectively permeable. Whereas semi can't choose. Okay? So yes, there is a difference. So remember once again, osmosis, water going from high concentration to low concentration, it's only water, as you know, and it crosses either a semi-permeable or a selectively permeable membrane, okay? All right. Now, obviously, it is important to maintain balance in the body. Homeostasis. It's a pity we're not doing endocrine system because we're talking about homeostasis again. Homeostasis is so important. It is very important to maintain your body's basic requirements, right? And to do that, you have to maintain a relatively stable internal environment, okay? Fluid balance is a part of a stable internal environment. So as it mentions here, water is essential to maintain fluid balance. It can go without food or water longer than water. Water travels from less concentrated areas to higher concentrated areas. This is stuff we know already. So water is essential to maintain fluid balance, absolutely. But remember, most of your chemical reactions occurring in your body have to do so, of course, in an aqueous solution. Okay? That's spelled wrong. Anyway, in an aqueous solution, which means your chemical reactions, hence your metabolic reactions, most of them require there to be liquid water in the cells for them even to happen, right? This is, of course, the reason why we strongly believe life cannot exist without water. Okay? Now, you can go roughly 3 days without water. Under special conditions, you can go as long as the record was 11 days. But understand that 11 days was under very, very specialized conditions. Okay? The person had the environmental temperature was relatively low, right, for those 11 days. The person did virtually no activity for those 11 days. And they were basically stranded at sea. Okay? And they were almost dead at the end. But keep in mind, this is 11 days of them laying down, basically sleeping 90% of the time, not moving at all. But on the average person cannot do more than 3 days without water before they die. Okay? Food, honestly, depending on how much weight you have walking around, you can go quite a while without food. Okay? On average, they said 2 weeks, but it's longer than 2 weeks. There was one guy who went a year without eating. Right? He was a fat guy like me, like myself. He pretty much just took vitamins and drank water for one whole year. Okay? So yeah, water, around 3 days, food can vary. 2 weeks, 2 months, a year, all over the place, right? Now, as important as water is, where do you get water from? Obviously, most of the water they come in the form of drinking. Okay? That said, pretty much all the food you eat is going to have a certain amount of water in it. I mean, even the toughest, driest Grace crackers, or I don't know if anybody know Jackass corn. You all know Jackass corn, eh? I want to assume you're Jamaicans. You must have seen a Jackass corn. As tough as that
Yes, sir.
is, yeah. I mean, I haven't had it in a while still. But even those are actually Jackass corn is actually a modification of something called hardtack. Oh, give me a second. It's a modification of something called hardtack, right? Which is what sailors used to take on ships with them as for food that wouldn't spoil. Now, also, of course, as I'm sure you know, that your metabolic reactions, aerobic respiration, produces 10% of the water in the body. So 10% of the water that your body needs on a daily basis, you produce it as you're making ATP via aerobic respiration, right? 10% is not a lot, so you still obviously need to drink, etc., but it's something. And that is where you would get the bulk of your water from, mainly from drinking fluids, some from food, right? Some foods are relatively low in water, as I mentioned here, the crackers and the hardtack. Some is very high in water, like watermelon, for example, cucumbers, these kind of things. but there's always water in there. And of course, you also produce water doing things like aerobic respiration, right? That said, how do you lose water? Obviously, what comes to mind for most people is going to be urine, right? Now, you urinate on average around 4 to 5 times a day, right? But anything up to 3 to 10 times a day, yes, 10 is still considered normal. Okay. And this, of course, is because different environmental temperatures will cause these things to fluctuate. Generally speaking, as long as you're urinating more than 3 times a day, and less than 10, you're in the normal range. But of course, 4 to 5 is closer to the average of that normal range, right? Now, another big way to lose water is perspiration, sweating. The more you sweat, the less you urinate because you're losing the water through the pores of your skin instead of via the urine, therefore you produce less urine, right? But remember when we're doing respiration, one of the things that has to happen is that when you're breathing, as air is passing in via your nasal cavity and down the larynx, pharynx, trachea, you're adding moisture to the air because the air has to be at 100% humidity by the time it gets down into your lungs because your lung tissue is super sensitive to dry air. But when you breathe out, there's no way for you to recover all the water vapor you put into that air. So therefore, breathing out, you lose water every time, right? So even if you did nothing but lie down and breathed, you'd eventually become dehydrated. Then of course there's feces. Now, or stool if you prefer. I prefer feces because stool sounds like something you can sit on. Now, feces, the amount of water in feces will vary from person to person, all right? Because of course, people who are regularly constipated, their feces actually has less water in it. And it's more compacted, that's why it's hard. And it's also hard to pass out. Okay? Um, Tears. I'm assuming most of you aren't big criers. I can't imagine y'all crying every day. But you do produce saliva. All right? Now, how do you lose saliva? People spit, right? Swallowing saliva is not a loss to the saliva. Obviously, it goes through your digestive system, and the saliva and the water in the saliva can be reabsorbed. But people spit a lot. There are quite a few countries where the culture actually promotes spitting. I won't name any country like that, but I know when I was young growing up, people used to spit all the while in Jamaica too. Until for the most part it was taken in hand. And there were even campaigns about not spitting and all kind of things, because spitting does have the potential of transmitting disease. Because when you do spit, you will actually leave small globules of saliva floating in the air, right? Just like when you sneeze, which can, of course, contain viruses, bacteria, etc., which can potentially infect other people. So you're not really supposed to be spitting all the time, but of course, we still do. Razimar mentions water loss via wounds and bleeding. All right, let me tell you why I haven't mentioned that one. The ones we're looking at here are what we consider to be the norm, all right? So these are the normal ways that you could lose water. You obviously, absolutely can lose it via injuries, right? But that's not normal, right? Thirst mechanism. You have osmoreceptors in the hypothalamus, okay? The hypothalamus is the most important gland in the body when it comes to um, regulating homeostasis. So it is constantly checking the concentration of your blood, is constantly getting information about your blood pressure, etc. Right? So osmoreceptors, of course, osmo, I'm sure you all have picked it up. as in osmotic, like osmotic concentration. Now, if your extracellular fluid is becoming hypertonic, as in there's too much solute versus the amount of solvent, or another way to put it, there's too much salt, not enough water in the blood normally or in your tissues, cerebrospinal fluid, the hypothalamus picks that up, realize that, hey, we're missing a lot of water. And what happens? You get a decrease in saliva because, of course, saliva in the mouth is water that is not in the blood. So of course, one of the signs of thirst is going to be dry mouth because you stop producing the saliva so you can direct the water to your blood. Right? Now, once the hypothalamus picks up the hypertonicity of your fluids, it is going to trigger thirst. Okay? And hormones like aldosterone, which would have been in the urinary system videos, will increase the hypothalamus's response to thirst, right? So when you first start secreting aldosterone, um, it is also going to trigger the thirst mechanism as well. Keeping in mind that, of course, the hypothalamus is going to be the one that is causing it. So you got start to get thirsty, hypothalamus picks it up, right? You start to release renin from the kidneys. Renin, of course, goes to angiotensin 1. You get angiotensin 2. Angiotensin 2 results in the release of aldosterone. Aldosterone then will cause lots of different things to occur, including, of course, thirst. Okay? So here we go. Renin angiotensin aldosterone system. RAAS. As we say in Jamaica, RAS, right? So renin angiotensin aldosterone system, as as we said, it's in the urinary system lecture, so we're not going to spend too much time on it, right? But let's just do a real quick run through, very, very quick, using the diagrams as I mentioned it before. So here we have the kidney. Kidney produces renin. Renin converts angiotensinogen to angiotensin 1, right? Let me make this a little bit bigger. I'm going to do a quick run through, but let's use the bigger slide.
Sir, when you run through, you can say it a little slow, please.
No problem. Okay.
Thank you.
So here we go. So remember, we're starting with the kidney now, right? It says sympathetic stimulation, hypotension, decreased sodium delivery. Kidney, so there's not enough sodium in the blood, right? Or the concentration of the blood is too low, it's too high. This triggers the kidney to release renin. Okay? Renin goes into the blood. Renin activates angiotensinogen. Remember, no gen normally refers to an inactive enzyme. So pepsinogen and trypsinogen, right, are inactive enzymes. So angiotensinogen is activated by renin in the blood to form angiotensin 1. So that's A1, okay? Angiotensin 1 has to go to the lungs. In the lungs, there's an enzyme called angiotensin converting enzyme. Remember, this is in the lung tissue. And once you get exposed to the angiotensin converting enzyme, it takes angiotensin 1 and it converts it to angiotensin 2. Right? Angiotensin 2 is then leaves the lung, goes back into circulation, and it can do several different things. Causes cardiac and vascular hypertrophy. Heart rate speeds up, your breathing rate speeds up. Okay? It then can, of course, trigger thirst. You can also affect the adrenal cortex, causing it to release aldosterone. It can also affect the pituitary gland, causing retention of sodium in the blood. Aldosterone, of course, will do the same thing, causing the reabsorption and retention of sodium in the blood. Now, why are we moving all of this sodium into the blood? Because water follows concentration gradients. If you increase the sodium concentration in your blood, water from the kidneys will flow into your blood, right? This, of course, causes an increase in your blood pressure. And, of course, increases the volume of liquid in the blood. All of which will, of course, correct your dehydration, right? All right. Hopefully that makes sense. Don't forget ADH, antidiuretic hormone, also causes a reabsorption of water from the collecting ducts of your kidneys, okay? Nephron specifically. And that, in a nutshell, is your renin-angiotensin-aldosterone system, okay? Pretty straightforward. No questions, so we can move on, right? This down here, vasopressin. Remember, vasopressin is the same as ADH. And vasopressin, once it's released by the pituitary gland, flows through your bloodstream, gets to the kidneys, gets to the collecting ducts in the kidneys, right? There it causes the collecting ducts to become permeable to water. And in diffusion allows the water, osmosis I should say, sorry, allows water to leave, and diffusion I should say as well, to leave your collecting ducts and flow into the interstitial fluid around the nephrons. And from there, that fluid goes back to your blood, okay? So between renin release in the renin-angiotensin system and the aldosterone production during that system and ADH or vasopressin, same thing, you can actively cause the reabsorption of water, okay? So if there's not enough water, if you're becoming dehydrated, these systems will respond to try and save water, to retain water, okay? Okay. Now, what happens when you have excess fluid deficit? Obviously, if you're losing more water than you're gaining, you end up with dehydration. And dehydration can eventually lead to hypovolemic shock. What's going on here? It means that your blood pressure is dropping rapidly because there's not enough blood in the system because there's not enough plasma. What's the big deal? If your blood volume drops too low, your blood pressure also drops. And if your blood pressure drops low enough, it can cause your heart to actually stop. You can actually have a heart attack because of low blood volume. Okay? So that's bad. You can, of course, treat severe dehydration or excessive fluid deficit, if you prefer, with IV fluids. Okay? You should never give somebody who is severely dehydrated pure water to drink. You can actually kill them with water. Sounds weird, right? But if somebody has severe dehydration, okay, it means that ordinarily it means that they've been sweating, right? So there's out in the environment, they're sweating, they're losing water. Then now on top of that, They find somebody finds them, gives them 2, 3, 4 bottles of drinking water. They knock back 2 liters worth of water in 10 minutes, 5 minutes, 8 minutes, whatever it is. What happens? All of this pure water rushes into their bloodstream, which of course causes their blood pressure to shoot back up, which sounds great, right? But remember, sweat contains not just water, but lots of sodium and other minerals. So when you drink all of this pure water after you've been sweating, you immediately get a crash in the osmotic concentration of your blood. So your blood goes from being too concentrated because it doesn't have enough water to being so to the osmotic concentration dropping so low that it can now actually start stripping your cells of electrolytes, which can actually lead to organ failure, right? So yeah, never give somebody who's dehydrated straight water to drink in abundance. You can kill them, right? Rosimar mentions coconut water. Coconut water has roughly the same osmotic concentration as blood, believe it or not. You can actually put coconut water in an IV and directly use that IV and put straight into somebody's veins. As long as the coconut water is sterilized, of course, your body will happily take it. So you're absolutely right. That's a much better solution. Um, Petra mentions salt and glucose to pure water. That works as well. Um, you must have heard of these things called rehydration salts. So you give the person water, plus you give them a rehydration salt tablet. The idea, of course, is that the rehydration salt will balance the osmotic concentration of the pure water, bring it to what is closer to that of your body, so that you can drink the pure water without worrying about hyper shock due to the low osmotic concentration, right? Overhydration, drinking too much water. Now, if you drink water in excess, you end up, of course, with hypervolemia. So in this case, you have too much blood. And what happens is that the extra fluid will tend to essentially leak out of your blood and move into your tissues, and you can get edema. Okay? Mentions there's edema, swelling of the ankles and the feet. Edema is not just swelling of the ankles and the feet, of course. Edema is just general swelling. But you will tend to get swelling of the legs relatively quickly with overhydration. Because of course, if you think about it, your legs, gravity has the greatest impact on things that are done in your legs. So it's easier for gravity to help squeeze water out of your capillaries into the tissues of your legs because the weight of of your blood is pressing down onto your legs, right? So it squeezes the water out more readily. You're less likely to get edema in your arms and legs in your arms, of course, because once again you're constantly moving them, and there's less pressure from your body being placed on it, right? Okay, that said, let's talk about some other substances that are going to impact um, the water concentration, the osmotic concentration in your body. Colloids. Colloids are, as this mentions here, they're large proteins that stay in the body for a long time, and they draw water from cells into the plasma. And this increases plasma osmolality, osmotic pressure. So albumin, as you know, is one of the biggest proteins you'll find in the blood. It is the kind of thing that you're talking about. Albumin helps to hold water in the blood, okay? Hence, plasma osmolality increases. Now, how can you use colloids in a medical setting? Mentions that colloids are used to treat hypovolemic shock due to burns. Now, burning is essentially severe dehydration, okay? when somebody gets their skin burnt, they're essentially drying out the cells until they die. What is a chemical burn or a heat burn or whatever it is? That's basically what's happening. The cells are drying out until they die. Okay? So you can lose a lot of water that way. And the damage can also cause water to start seeping out of your tissues. So even after you've been burnt, the burned areas will essentially crack and fluid will continue to seep out of your tissues, which will further dehydrate the tissues even after you've gotten the burning under control. So what do the colloids do? When you give a burned patient water and you give them colloids too, it helps to keep the plasma inside their blood. So it's not lost due to the burns. Okay? And no surprise if a person is hemorrhaging, they're losing blood from a wound, internal bleeding, whatever it is. Colloids, once again, will help to keep the water in the blood vessels, right? And no surprise, after many surgeries, you have a loss of fluid. Colloids help to keep fluid in the blood, right? Then now you have crystalloids. So crystalloids are electrolytes that are used, of course, in fluid replacement. But they're also going to promote increase in urine output. And what they do is they increase the rate of diffusion across your cell membranes, right? And because of that, fluid will more quickly leave the plasma and enter the interstitial fluid. So why would you want to do that? You're drinking water. You're trying to think of it this way. You're trying to flush a person's system, as they say in Jamaica. You want to flush out maybe there are toxins in the body. You want to get the toxins out, and you want to replace that toxin-laden fluid with fresh fluid. So crystalloids, you take the crystalloids, you drink, you also take an IV fluid. Crystalloids help to push out the fluid that's in the blood already, send that to the kidney so you can urinate it out. And then it makes it easier now for the IV fluid to come in and take its place, right? Keep in mind, I'm trying to simplify the whole thing, right? So it mentions here crystalloids can be used to replace electrolytes, right? And it, of course, increase fluid volume in the body. And it mentions that the compartment which is most expanded depends on the solute. That means that crystalloids can be used to increase the volume of the intracellular or extracellular compartment, depending on the type of crystalloid you're using, right? All right. Parenteral solutions. The idea, of course, now is you're trying to equalize the concentration of fluids in the body. You're trying to promote essentially isotonicity. Okay. So you want the fluids in the person's body to reach where the concentration that they're supposed to be at. So you can get that isotonic balance, right? Remember, we're all about balance with osmosis and diffusion, right? So you can replace extracellular fluid that is lost. You can, of course, stabilize a person's blood volume, right? Now, the idea here, of course, of the parenteral solution, you don't want to overhydrate or underhydrate. You want their hydration level to return to what is essentially normal, okay? So you want the parenteral fluid has to have enough electrolytes in there to replace the ones that you've lost, but not to um put too many in there. So you go from having too few to having too many, right? Which is why it says there no movement into or out of the ICF should occur. So you're trying to impact, therefore, the extracellular fluid more than the intracellular fluid. All right. What can you use these isotonic fluids like the parenteral fluid for? It mentions here you can use them for blood transfusions, okay? So see if this makes sense to you. So you go, you get a blood transfusion, they take out 1 unit of blood, so that's 500 mils. You're now 500 mils down. Your body, of course, will eventually replace the blood cells. You will, of course, also release some blood cells from the spleen, but you're still missing plasma. So if you give someone some of this isotonic fluid, it means that the fluid is at the proper balance of solutes versus solvents. So when you put this into the person's blood, you will increase their blood volume without affecting the tonicity of the person's blood. Okay? So that's one thing. So you increase the blood volume without affecting tonicity. It also mentions to treat metabolic alkalosis. Metabolic alkalosis is referring now to your blood being too alkaline due to some metabolic processes. Okay? It's normally associated with kidney or liver failure. Okay? Kidney or liver failure tends to lead to metabolic alkalosis. Right? So intravascular dehydration can also be treated. Or of course, intra is within, okay? As you know. So if you're losing water and the water is being pulled from your blood cells, your tissues, your cells are becoming dehydrated. So therefore, isotonic fluids can help to rebalance the concentration of fluid inside your cells, right? That said, you would think that an isotonic fluid, which is essentially designed to be at the same concentration as your body's tissues fluids, it should be safe. And actually it relatively is safe. That said, if you put too much fluid in a person, even if it's isotonic, even if the concentration is just right, you will of course potentially cause a circulatory overload. You increase the pressure in the blood, the blood pressure, which can of course lead to organ damage. Okay. It also mentions diluting the concentration of hemoglobin as well as the hematocrit, which of course will reduce the efficiency of the blood when it comes to transporting oxygen. All right. So this little video here will help to explain the difference between hypertonic and hypotonic, but I think for the most part, you understand, right? So let's look at tonicity now in terms of directly in terms of the body, in terms of the fluid compartments, right? So hypertonic solutions. Remember, if a solution is hypertonic, its osmotic concentration is greater than that of what you'd expect to find in the cells, okay? So because of that, water will leave the cells and move into the solution, which causes the cells to shrink. Now, if your cells are shrinking, it means you're losing fluid from your intracellular compartment, and that fluid is moving into the extracellular compartment. So that's a fluid shift. So hypertonic solutions, when given to a human being, can cause a fluid shift. So this can lead to intercellular dehydration because you're pulling water out of your blood, out of your tissues and putting them into the interstitial spaces instead, right?
So you can repeat that one more time,
All right.
please.
If you give somebody a hypertonic solution, right? One of the things that can happen is that because the hypertonic solution is more concentrated than the tissues, When that solution gets to the tissues, that solution will pull water out of the cells of the tissues. This causes a fluid shift, causes water to leave your cells, flow into the tissue fluid around the cells, right? And that, of course, results in cellular dehydration, okay? So hypertonic solutions can cause cellular dehydration, is what I'm saying, right? And remember, fluid shift from intercellular to extracellular compartment, as the fluid is moving from inside the cell to outside the cell, right? That said, hypertonic solutions do have a function. They're not completely useless, right? It mentions here intravascular dehydration and interstitial overload. See if this makes sense to you. Let us say you have somebody with severe edema, okay? They have water in their tissues, so they're bloated, okay? Them swell up. You want to be able to draw the water away from the tissues and direct the water elsewhere. Or if you have a case where when you have intravascular dehydration, so the plasma the volume of plasma in the blood is too low. If you give a hypertonic solution, it actually pulls fluid from the surrounding tissues and directs that fluid into the blood, right? So somebody with severe edema, swelling, you give them the hypertonic solution, and it literally draws the fluid out of their tissues, sends that fluid to the blood. And of course, if the fluid is in excess from there, the kidneys can get rid of it. Okay. Now, I want to say something that sounds weird, but see if it makes sense to you. Because this happens to some women. Some women during their periods they get bloated because they get water retention. Okay. And what you have happening is that a lot of these women who get water retention also start craving very salty food, salty snacks during this period. And one of the reasons for it, of course, is that those salty snacks help to make their blood hypertonic. And the hypertonic blood reduces the rate at which the edema will caused by their menstrual cycle will impact them body, right? Can actually pull some of the water back from their surrounding tissues and direct that fluid back into the blood. So it can reduce swelling during menstruation, right? Now, that said, as I mentioned, it draws fluid out of edematous cells to plasma, decreases cellular edema, raises blood pressure, right? And increases urine output. I think I explained how all of that happens already, right? And of course, hypertonic solutions are going to be loaded with minerals, which means that it can replace electrolytes as well, okay? And we already mentioned that fluid will be excreted by the kidneys. All right. Now, what are some issues that can arise from giving somebody hypertonic solutions? Or if you consume too many hypertonic solutions, you can have circulatory overload. Too much fluid gets moved into the blood because the blood is so osmotically concentrated, right? So your blood pressure shoots right up. You can even cause irritation to the internal walls of your blood vessels because of all of the minerals, etc., in the hypertonic solution. Now, elderly people in particular, you have to be careful because they have a tendency of retaining water as a stress response. So if they're returning water as a stress response and you give them strong hypertonic solutions and you start drawing this water out, you can go from them retaining a little water to giving them intercellular dehydration, which for an older person can stress them enough to kill them, right? So you have to be careful. What about your hypotonic solutions in a medical scenario? So it mentions here, if you have concentrated salt in the intracellular spaces, it's going to cause dehydration, right? So water will move into the cells to counter that. This causes the cells to swell and shift fluid from intravascular spaces into intracellular fluid. Simply put, your cells have taken up too much salt, okay? There's too many minerals in your cells. So therefore, the fluid inside your cells is too concentrated. High osmotic concentration. This can damage the cells. A hypotonic solution, of course, will have more water in there than your cells will. So that water will leave the blood, travel into the interstitial fluid, and from there it will flow into your cells. This increases the volume of the cells for sure, but it also reduces the osmotic concentration in the cells. Of course, if you overdo it, you can damage the cells and you can as well, right? But you can cause fluid to shift from intravascular spaces into the intracellular fluid. So fluid around the cell can move into the cell, right? So what can you use a hypotonic solution for? Cellular dehydration, as we mentioned before. So if your cells have lost too much water and you need to quickly rehydrate them, hypotonic solution is good for that. And of course, you can also replace electrolytes. You can also lower your sodium levels because the hypotonic solution is going to be added to the interstitial fluid. This, of course, means more interstitial fluid. Automatically, if you have more volume of fluid, the same amount of sodium, you automatically reduce sodium concentration, right? And of course, the hypotonic solution means that your more urine will be formed, okay? And of course, the hypotonic solution will, as it says, it provides free water, and there will be some sodium and chloride in those types of solutions anyway, right? And of course, hypotonic solutions will add to your daily water requirement. So if you're drinking hypotonic solutions, you're adding water to your cells, you're adding water to your body, you're increasing urine formation, so you're helping your kidneys to function properly, right? Now, once again, hypotonic solutions, if you drink too much of them, can cause a significant increase in your blood pressure, but remember, it can also cause a drop in osmotic concentration in your in the blood plasma, which can have a wide range of impacts, right? All right, that said, I'm done with tonicity. Let's now talk about some electrolytes. Electrolytes are sort of are one of these things that you hear every day. For a long time, you couldn't get away from electrolytes. But what really are electrolytes? Most people have no idea, right? All an electrolyte is, in the face of it, is this. An electrolyte refers to a substance that can affect your body's osmotic concentration. That's all it is, okay? So electrolytes can affect your body's osmotic concentration. They're normally charged particles. Quite a few of them are minerals, but they can be proteins as well, okay? That said, sodium is the major electrolyte of your extracellular fluid. Remember, you have a whole heap of sodium outside cells, right? Where do you get sodium from? You get it from your diet, salt. Remember, sodium chloride, table salt, right? Very important. Now, you lose sodium, of course, via kidney excretion, And sodium, of course, can be used to help to control your body's water. Remember, renin angiotensin system, by reabsorbing sodium, you reabsorb water as well, which of course means conversely, if you secrete sodium, you also increase water removal as well. Okay. It mentions here, well, we'll leave that for now. Sodium, of course, is involved, as you know from AMP1, in nervous system, as well as muscle, as well as glandular functions, right? Remember, you need that depolarization refers to the flow of sodium into a cell, right? Without depolarization, muscles don't work, nerves don't work. Sodium can also help to regulate pH as well as the isotonicity of your body's tissues, right? pH because sodium can be swapped with protons, right? In the urinary system, you can do a antiport system. In antiport, you take sodium and you pass sodium into the body. At the same time, protons are swapped out of the body. So simply put, if you have too many protons in your blood is too acidic, you swap the sodium in the kidneys with protons, then you pee out the protons. So you have now removed excess protons from your body that way, right? It's an anti-port because you're moving sodium in one direction and moving the protons in the opposite direction, okay? So you can just use sodium to help you to regulate your body's acid balance, right? The mentioned sodium also combines readily with chloride and bicarbonates, which also helps to promote acid-base balance. So it can regulate pH as well as promotes acid-base balance as well, right? Now, hyponatremia. Of course, as you know, normally when you say the term hypo, it means less than or not enough, right? So in hyponatremia, you do not have enough sodium in the body, right? So what are the symptoms of low sodium? It mentions here, you can get hyponatremia from excessive sweating or intaking large volumes of water. But of course, these days, if let's say you're one of these people who are very, very conscious of health, and you have all of these very, very low or no sodium products, and you spend all your money buying these things, you don't eat anything with any sodium in there, you can induce hyponatremia by doing that, right? So you also can have issues with adrenal insufficiency. So your adrenal glands are not functioning properly. You're not releasing enough aldosterone to reabsorb sodium. That can lead to hyponatremia. GI suctioning is a medical condition. Medical, this is done basically, you're flushing the GI tract, which can cause loss of sodium. Diuretics. Remember, diuretics cause increased urination. Sodium is in urine. So anything that increases the flow of the loss of urine will also increase the risk of hyponatremia. And of course, surgery. You lose too much blood, you lose too much tissue fluid, you can get hyponatremia, right? So what is clinically the definition of hyponatremia? If you have a sodium level of less than 135 millimoles per liter, you have hyponatremia, right? What are some of the symptoms? Gastrointestinal discomfort, nausea, vomiting, headaches, as I mentioned, a throbbing headache, restlessness, you might get swollen hands and feet, lethargy, confusion, wheezing, etc. Can even go as far as to give you a coma and death. So severely low sodium levels for a long enough period of time will actually kill you, right? Now, that said, we do consume a lot of sodium on a day-to-day basis. Most of us are not in any danger of getting hyponatremia, right? At least not from diet. All right. So a couple of other symptoms we did mention. Hypotension, vomiting, we mentioned vomiting, diarrhea, and seizures are some other symptoms as well, right? How do you treat hyponatremia? You give the person normal saline. Normal saline basically has the equivalent of the percentage concentration of sodium that your blood is supposed to have. Okay? So in this case here it's 0.9% or roughly 1%. So pretty much normal saline is 1 part sodium but 99 parts water. Roughly, right? Then now we have hypernatremia. So if hypo was not enough, hyper, of course, is going to be too much. Okay? Hypernatremia, excessive use of saline infusions. Right? Some people, for example, use saline washes. Some women will use saline as douches. So they wash out reproductive organs with the douche. Some people will do flushes of the nasal cavity with saline water, for example, things like that, right? Some people will take traditional medication that is in very salty water. So these are the kinds of ways you can cause excessive increases to your sodium level. And yes, obviously, extremely high consumption of salt in your diet can do the same thing, right? But if you have a reduction in water consumption, can also lead to hyponatremia. Why? Remember, you're not drinking enough water, what's going to happen? You're going to have an increase in the production of ADH or vasopressin, same thing, an increase in the production of aldosterone. Aldosterone in particular is going to cause an increase in sodium levels because you have to reabsorb the sodium in order to reabsorb water. So as long as you are dehydrated for excessive periods of time, can actually also lead to hypernatremia. Even some drugs can cause it. Mentions here cortisone and cough medicines can actually lead to hypernatremia. Obviously, this is abuse. I don't know if you know this, guys, but certain cough medications, right? I won't mention which ones, but if you drink enough of it, you can actually get high. And people have been known, and it's a real thing, to get high on cough medicine. They can't get anything else. So yeah, sometimes people do drink excessive quantities of certain types of cough medicine, which can of course lead to hypernatremia. So they're trying to get high by drinking cough medicine, they get hypernatremia instead. Now, if you have an excessive fluid loss without loss of sodium, you can also get hypernatremia, right? Now, signs and symptoms of hypernatremia. Edema, hypertonicity, so your blood is very concentrated, red flushed skin, as well as dry, sticky membranes. So we're talking about in your mouth, in the Madam Sutherland, I'm not going to say. If you all need to know, you're going to go do the research, and I'm not going to tell you which cough medicine will make you high. Just in case. But yeah, so if you're hypernatremic, you're gonna have sticky membranes. Your mouth will feel dry. Your nasal passage will feel dry, right? Even the mucus that comes out of your nose will be very sticky, right? And no surprise, you're gonna be very thirsty because your blood is very concentrated, right? Elevated body temperature can also happen. And no surprise, with all the sodium in your blood, your urine concentration, urine production is going to drop as well. So how do you treat hypernatremia? First of all, taking less salt, right? Taking less salt. You can also take dextrose 5W. That's 5% dextrose in water. Remember, dextrose is basically a type of sucrose, right? It's basically sugar and water. It mentions here that, so if you take the dextrose and water, it will promote diuresis by excretion of both salt and water from the blood. Simply put, you take the dextrose solution, you make more urine, more sodium gets put in the urine, hence automatically, of course, you get less sodium, right? Nice and easy. And yes, very, very salty food can increase your risk of hypernatremia for sure. But here's the thing. If let's say you're somebody who loves them some saltfish and chips and all of these things, but you drink a lot of water, you will not become hypernatremic, right? Because as you're consuming the high sodium, you're drinking the water to produce high volumes of urine. Therefore, one balances the other. If you happen to have a high sodium diet, right, and you're not drinking a lot of water, then you can worry about it, okay? But for the most part, as long as your kidneys are functioning, have all the salty snacks you want, just drink plenty of water, you'll be fine, right? As a matter of fact, I think I probably mentioned it before, sodium actually has no long-term impacts on your blood pressure. So all of these years when people have telling you that salt causes high blood pressure, it is not the case. We now know for a fact salt does not cause long-term high blood pressure. Acute, short-term high blood pressure, sure, it can. So if you consume lots of very, very salty food, all right, and then drink plenty of water shortly afterwards, your blood pressure will go up briefly, then you urinate it out and it goes back to normal, right? So have all the salty food you want, just drink plenty of water with it, okay? All right, potassium. Potassium, of course, as I'm sure as you know, is now going to be found in your intracellular compartment, okay? So it is the major electrolyte of your intercellular compartment. And as I'm sure you know, potassium is also very, very important. We know potassium is important in muscle contraction because we did it in AMP1. You know, potassium is important in nerve conduction. We did that in AMP1 as well, right? You know, of course, potassium is also involved in enzyme activity. It can be used to activate or deactivate enzymes of specific types, right? So it mentions here amino acids to proteins. So, and also has functions, of course, in your cell membrane as well. So potassium is very important, just the way sodium is very important. But remember, sodium is the most important extracellular electrolyte, and potassium is the most important intercellular electrolyte, okay? That said, hypokalemia. Hypokalemia, of course, once again, not enough potassium. So some people do not store potassium well in their bodies, right? But that's fairly rare. But you can also have people who get ill, they go to the hospital and they're given IV fluids. If they're given too much IV fluid without potassium in it, can also cause hypokalemia. Diuretic therapy. If you're causing extreme urination in a patient, or if you're doing it to yourself, some people do, can also cause hypokalemia. But one of the probably the most common way with hyperkalemia is simply not taking enough potassium in your diet. Okay? Now, as important as potassium is, I probably half of you couldn't tell me 3 food items that have potassium in there, without using banana, right? If you didn't have to say banana, what else would you find potassium in? Who can give me two? No banana. What else do you find potassium in? Potatoes. No. No, sorry, no. The skin of
Sir,
the
pumpkin.
potato. The skin of the potato. If you peel the potato, you're basically wasting time. But there's a decent amount of potassium in the skin. So like if you're doing like home fries, that's great. Spinach, yes, that's a good one. Green veg tend to have potassium in there. Kiwi, somebody mentions kiwi. Justine, kiwi, yes. Sour fruit also will tend to have potassium in there. Salmon, fish, yes. Mango, but once again, particularly skin. So yeah, I guess I was wrong. You all know some things, man. Good. Yes, Ayana, that's a good one. Legumes in general, so lentils and beans and peas will also have plenty of potassium in it. Papa, yeah, avocado too, yeah. Good. Excellent. So I was wrong. All right. Um, last time I asked this question, the one thing that I got back was banana. So I'm good. I'm glad to see that y'all are better than that. Okay. So that said, um, hyperkalemia in a little bit more detail. So I mentioned poor absorption. So that's steatorrhea. You have vomiting, can cause hyperkalemia as well. GI suction or drainage, once again, you're flushing the system, right? And extensive burns. Now, what are the signs and symptoms of hyperkalemia? You'll notice that diagram over there on the right side is a EKG, right? Of course, why? Because potassium is involved in the contraction of muscles, and your heart, of course, is obviously made of cardiac muscle, right? So what's going on here? We have dysrhythmias. We have abdominal distension, so the belly get big. Soft and flabby muscles because potassium is involved in maintaining muscle tone, right? So if your muscles are started to be flabby, your heart is beating irregularly, and you get a big belly, it normally means you are hypokalemic. Hyperkalemia is, of course, really easy to treat. You just got to consume things with potassium. So the avocado and the broccoli, honestly, I'm not too sure about the salmon. Kiwi and the spinach, those things, absolutely, right? And of course, how does lab work treat it? It doesn't. But it allows you to identify that it's happening, right? Milk is another good one. Should I mention milk? So hyperkalemia. You got too much potassium now. So what's going on? Some people take potassium salts to treat various things, right? A lot of this stuff is I don't want to say it's unfounded. Let's call it traditional medicine. A lot of traditional medicine things um will have things like potassium salts in there. Okay. Oh, you know another good place to get it? Preserved meat, which of course for most people equals bacon. Bacon can also be high in potassium and nitrates as well, right? Too high in some cases, particularly the nitrates, but potassium as well. Um, Also, acute renal or even chronic renal failure. You're simply not able to remove the potassium from the bloodstream, so it, of course, builds up over time, right? Then we have metabolic acidosis. So I'd mentioned to you before, metabolic alkalosis or alkosis is caused, of course, by the inability to remove alkaline chemicals from the body. Normally, this is due to the failure of the kidney or the liver. Okay? Metabolic acidosis is definitely associated with diabetes, but it is also associated with kidney failure. And diabetes, uncontrolled diabetes, does cause a significant increase in your risk of kidney failure. As a matter of fact, most of the people in Jamaica with kidney failure also have diabetes, right? So those two are linked together. So kidney failure, diabetes can result in metabolic acidosis. Once again, you can't remove um, the excess potassium as well as other substances from the blood, so you end up with hyperkalemia, right? Yes, potassium supplements. You do have people, once again, who abuse these kind of medicines. But by the way, I'm going to assume everybody knows this, but let's make sure. Can I assume, especially since there's lots of pharmacists in here, you know the difference between a pharmaceutical and a nutraceutical? Can I assume everybody knows that? If not, let me know, please. Okay, good. Because this is a nutraceutical. Oh, sorry. Okay. Two people said no. All right. I'm going to give it to you in a nutshell. Pharmaceuticals refers to drugs that have been proven to have an impact on human physiology. Okay. The side effects are well known and documented, and they have been cleared for human use under specific conditions. Okay. So that is like your Panadol. It doesn't have to be over the counter. It can be over the counter stuff like Panadol or Claritin or any of these things, right? Those are pharmaceuticals. They're tested. We know they have an impact. We know roughly what the impact is. We know how to utilize them so as to make sure they're not dangerous, okay? So they are regulated. So those are your pharmaceuticals. Nutraceuticals are nonsense. Nutraceuticals can make any kind of claim. The claim does not have to be proven. They're not regulated the way pharmaceuticals are as well. And dosing, because they're not properly regulated, even the dosing itself is not properly known. So for example, um, let's take Cersei. Everybody knows people drink Cersei tea, right? And you know you can buy Cersei tea in the powdered form now, or you can buy it in tea bag, right? Cersei is known to cause kidney and liver damage. Okay? But it is a traditional nutraceutical. It is something people take for health reasons. So it's not simply a tea, right? It's a traditional nutraceutical. And because it is a nutraceutical, it is not regulated. There's no dosage information. If you buy Cersei from some random company and you drink Cersei until you get kidney failure, you can't turn around and sue them because it is not a regulated substance, right? So there's no dosing that is acceptable. Okay. So lots of very dangerous things are on the market as nutraceuticals. And because they're unregulated, basically anybody can sell them, right? Many people die from use of nutraceuticals. They're extremely dangerous in some cases. In other cases, they're utterly useless. As in, they're selling you what amounts to snake oil. Once again, because there's no control. There was this guy in Jamaica a few years back that was selling an immunobooster. Was it immunogizer, immunobooster, whatever it is? And the person claimed it could fight HIV, flipping AIDS. This one was basically saying if you took his immunobooster, immunogizer, whatever it was, it would make your HIV better. Obviously, that is garbage. But because he was selling it as a nutraceutical, you could actually run ads that made that claim and it was legal, right? So yeah, it's in a song. I know there was an immunogizer or immunobooster song at one point. I think I heard it as an ad, but yeah. So you have to be really careful. Nutraceuticals can be extremely dangerous or utterly useless. And because the government doesn't regulate them, you have no idea which, right? Anyway, hopefully I didn't go too long. I know it's 6 o'clock now, but give me another 30 minutes, please. So let me at least finish this and then we can move on. Colloidal silver. Oh my God. Silver water is complete nonsense. Colloidal silver water is utter nonsense. But guess what? It doesn't have to be able to prove that it can do anything. It's a nutraceutical. If you want to believe it, you believe it. If not, then you can't claim against them for it. You can sue a pharmaceutical company. You cannot sue a nutraceutical company. You're on your own where they're concerned. All right, signs and symptoms of hyperkalemia. Tachycardia is one. So of course, this means your heart rate is faster than it should be. That's where the tachy part comes in, right? This can lead to cardiac arrest, ventricular fibrillation. They can lead to numbness and tingling in your extremities. So your fingers and toes get tingling sensations in them. Oliguria. Remember now, anuria, oliguria, different things. Anuria means you produce no urine at all in a 24-hour period. If you produce zero urine in one day, you have anuria. Okay? If you produce less than 500 mils of urine in one day, you have oliguria. Anuria is an extremely bad sign. If you produce no urine in one whole day, either you're dehydrated severely or your kidneys are playing the way they should, which is bad, right? Oliguria could be a sign that you need to drink more water, or it could be a sign that your kidneys are failing as well, right? But normally it's a sign, but it's less likely. But if it's anuria, you're caught a doc. Abdominal cramps is your often abdominal cramps comes up. Muscle weakness, of course. Neuromuscular function decreases, right? And this is looking at ventricular fibrillation. Remember this, the ventricles, QRS, here's the QRS. You can see how deep the trench in the QRS is, right? So basically the heart, the ventricles give you what they call a sawtooth appearance. So the heart is beating rapidly, but the QRS here is very deep. So I say it looks like a sawtooth. Okay. So how do you treat hyperkalemia? Obviously, if you're taking drugs that are containing potassium, you need to stop. I think that's fairly obvious, right? Stop taking all the potassium. You can also take hypertonic dextrose with insulin in it. This helps to push the potassium out, assuming your kidneys are working. Sorry, this pushes the potassium into your cells, I should say. My apologies. So hypertonic dextrose, insulin actually pushes, as I said, the potassium into your cells. But this, of course, is only briefly. So if you need to drop your potassium level like immediately because of the tachycardia, then you could take a medication like that. There is, of course, danger to it. Okay. It also mentions a drug called K-exalate as well, right? That you can take. And diuretic therapy. Once again, if you increase the urine production, you're going to lose sodium as well as potassium. But of course, if your potassium levels are dangerously high, you might as well lose the sodium too, right? You can always get IV fluid for the sodium if you need it. All right, so pH now. Obviously, we know pH refers to acidity versus alkalinity, right? Now, generally speaking, an alkalinity of 7 is neutral, as you know. Above 7 is alkaline, below 7 is acidic. But that is not for the body. Remember, for the body, your standard pH, your basic pH, generally speaking, is 7.35 to 7.45 for most of your body's tissues, okay? So when your body is trying to maintain pH balance, that's where it's trying to stay, right? Now, how does your body try to maintain this pH? There's several different things you can do. One of them is the use of buffers. As I mentioned here, buffers are chemicals that help to maintain normal body pH, okay? Um, Also, bicarbonate ions are also going to be something that be used, as well as phosphates. Um, Basically, what you're doing is you're absorbing or secreting these substances, which will help to balance your body's pH, okay? For example, obviously, if your blood has a pH of 7.3, that's too low. So you can reabsorb bicarbonate ions from urine, send it to the blood, that causes your blood pH to increase. If your blood pH is 7.5, of course, you want to secrete bicarbonate ions, get rid of them, and reabsorb protons to compensate. Okay? What is resonium medication? I've never heard of that. Okay, so removal of acids. These are the two main ways you get rid of acidic substances in the body. You breathe them out via the lungs, or you urinate them out. Okay? Because of that, we have respiratory acidosis, sodium polystyrene, what's that for? And metabolic acidosis. Okay? If you are not able to remove carbon dioxide quickly enough from your body, it will cause, of course, your blood to become acidic. And because the cause of it would be the buildup of protons due to carbon dioxide, that is respiratory acidosis. Okay? Because you should have been able to breathe out the CO2. If instead your decrease in pH is due to your inability to remove protons that are produced from metabolic reactions, like in the digestive system, for example, in digestion, but you can't urinate them out fast enough, then that is metabolic acidosis, right? So remember now, don't confuse those two for me, please, right? Oh, resonium is used to treat hyperkalemia. Okay. So sodium polystyrene is the active ingredient in resonium. Okay. I'm not too familiar with resonium. Interesting. All right. So remember now, the two types of acidosis, right? So you can see here on this little seesaw, we have carbon dioxide level and we have pH. What does this tell us? It tells us as CO2 levels rise, carbon dioxide causes that depression in pH. Hence, respiratory acidosis, okay? And of course, if CO2 levels drop dramatically and very quickly below what they should, your blood becomes too alkaline. And that can cause, of course, respiratory alkalosis instead, okay? Of course, with bicarbonate ions, as your bicarbonate ion concentration increases, the pH increases as well. Because bicarbonate, they're alkaline, right? As bicarbonate ions decrease, your blood's pH will also decrease, all right? So remember, normal range 7.35 to 7.45, right? If you have acidosis, whether it's metabolic or otherwise, what are the symptoms? Sleepiness, coma. So many of these conditions could just knock you right out. Disorientation, dizziness, headache, seizures. These look very similar to what you'd see if you had hyperkalemia. All right. So sometimes symptoms alone are not enough for a doctor, a medical professional to be able to target what's wrong with you. That's why blood tests are so important, right? You can't just go on symptoms alone. Now, if you once again remove bicarbonate ions too rapidly, you can also cause acidosis. So excessive vomiting can cause that. Continuous GI suctioning, once again, you're continually sweeping on the gastrointestinal tract. Diuretic therapy, you're peeing too much, right? And it can also cause hypercholesterolemia. It can also cause hypercalcemia, right? And of course, patients on a low sodium diet can also end up with a low bicarbonates as well. Okay. This so this is looking at sodium bicarbonate now as a drug. I mean, of course, when you think of sodium bicarbonate, most people think baking soda. Okay. But as you can see here, it can be used for other things. For example, it can be used to treat people who are taking too many acidic medications, right? It can result in alkalization of urine, and this results in less acid reabsorbed. So it helps to flush acid from your systems. It helps to hold acid in the urine as well, so the acid won't be reabsorbed. It can help to neutralize gastric acid if you're having issues with gastric acid overproduction. That said, if you take too much of it, it can lead to alkalosis. Now, a lot of people, especially older people, when they have like gas, which is not really what you should be using it for, or they have acid stomach as we call it, they will take a glass of water and put about half a teaspoon of baking soda in the water, mix it up and drink it. Okay? And it absolutely does neutralize the stomach acid. It actually does. It's pretty much what Tums is doing. But with half a teaspoon, it's pretty strong. So you can imagine somebody who has recurring acid reflux, taking baking soda once a day, twice a day, over a period of time, it can of course lead to alkalosis. Too many bicarbonates end up in their blood because of it, right? So what can alkalosis cause? So a pH of above 7.45, irritability. That's another one we see often, you know. Confusion again. Here we have cyanosis, slow respiration, irregular pulse, muscle twitching. Now, if you think back to when we were doing respiratory system, and I mentioned respiratory alkalosis or alkalosis if you prefer, I mentioned to you when it comes to alkaline shift, um, the more alkaline your blood is, the more oxygen it picks up and the more strongly it holds on to that oxygen. So if you consume lots of alkaline substances, your blood picks up whole of oxygen. So when your blood is passing through the chemoreceptors in your aortic and your carotid sinus, it will read that the blood is high in oxygen levels, right? Plenty of oxygen. And that feeds back to the hypothalamus, which feeds back to the medulla, which then causes your heart rate to go down. It causes your breathing rate to go down. Because as far as it's concerned, you have a whole heap of oxygen in the blood already. You don't need any more. So you don't need to be breathing as fast. Right? So alkalosis slows everything down, breathing rate, heart rate. Right? Also increases the risk of muscle twitches, irregular pulses. Some people also get muscle cramps as well, right? How do you treat it? You can pretty much give them potassium, ammonium chloride in severe cases, and anything that in cause an increase in secretion of bicarbonate ions will of course help. In the case of life-threatening alkalosis, where the patient has consumed so much of an alkaline substance that their heart is actually on the midst of stopping, you can give them ammonium chloride. But the thing is, ammonium chloride itself is toxic and can lead to bradycardia, twitching, and convulsions, and it can actually potentially cause you to have a heart attack as well, right? All right. So obviously, what we're doing here for electrolytes is a very truncated electrolytes lecture. We've left out things like and the manganese and magnesium and calcium. We're concentrating on just a few things, okay? To make things a little easier for everybody. So if you're wondering why I haven't mentioned those things, that's the reason why, okay? That said, we need to talk about the buffer system now. The buffer system obviously is going to feed in to your acid-base balance. So how does the buffer system work? First of all, remember what a buffer is. A buffer refers to a substance that resists changes in pH, right? It doesn't like to be too alkaline. It doesn't like to be too acidic, right? If you put a buffer in an alkaline environment, it will produce an acid. If you put it in an acid environment, it will produce an alkaline substance, right? So what are the types of buffer systems you'll find in the body? There are three of them. You have the phosphate buffer system, which is particularly important for intracellular fluid and urine. So pH of intracellular fluid and urine, that's the phosphate buffer. Remember, phosphate is found in large concentrations inside the cells. So that makes sense, right? You have the carbonic acid bicarbonate buffer system. This is mainly for extracellular fluid. So this now is basically carbon dioxide plus water to give us bicarbonate ions plus protons. So remember what this is. This is basically transporting carbon dioxide in the blood, as you should remember, right? Which is, of course, why it's fully reversible. Once you form the carbonic acid and you get the bicarbonates and a proton, you transport this, of course, to the lungs, you reverse everything, get back your oxygen, your carbon dioxide, your water, and you release the carbon dioxide, right? It also mentions here that bicarbonate reserves, right, can also contribute to the overall buffer system in the carbonic acid buffer system, right? Then now we have the protein buffer system. Pretty much certain proteins are can change configuration depending on the pH they're in. Okay. Here's the basic idea. let's see. Sorry, give me one quick second here. I will soon finish. I will soon finish. All right. Do you all remember what an amino acid looks like? Let me just bring this up. So what you're looking at here is a carboxyl group, an amino group. You have the central carbon here. We're now somewhat worried about the side chains here, okay? What is important here is the amino group and the carboxyl group, okay? Because the configuration of those two groups is affected by pH. So let's say we have an amino acid. So let's say we have NH2 and we have our C here. And then of course on the other side now, we have our COOH, right? Right? When you expose an amino acid like this to an alkaline environment, it will lose the proton here, okay? So this will leave and enter solution. So basically, if you expose an amino acid to alkaline environment, it will attempt to turn the environment back, right? If you put it in an acidic environment, you can actually gain a proton on the amino side here, like that, temporarily, okay? So you can pick up or release protons. This, of course, means you can affect the pH of the environment that your amino acid is in. Just to solidify that, I'm going to show you this thing here. Give me 1 second. All right. What I'm describing is what is referred to as a zwitterion, right? So it shows you here the configuration of amino acid under acidic conditions, okay? So we have NH3 here. We have COOH, okay? So you have gained a proton. So under acidic conditions, it absorbs a proton, making the solution less acidic, even though it makes the amino acid itself more acidic, right? So it's capturing a proton. If you change the pH that the amino acid is in to a neutral environment, it releases a proton. So you end up with a negative charge on one side and a positive charge on the other side. So overall, the charge is 0, right? So it's neutral. So in an acidic environment, it becomes acidic. But remember, by attaching itself to that proton, you reduce the acidity of the environment. In a neutral environment, it stays neutral. In an alkaline environment, it releases protons. So instead of having NH3 here, we now have NH2, and it becomes alkaline. But by releasing the proton into the environment, you make the environment more acidic, right? So depending on the pH that this protein is in, it will resist changes, right? You put it in an acid, it soaks up acid. You put it in a base, it releases acid. And I'm talking about, when I say acid, of course, I mean the proton, okay? So that said, of course, we'll jump back to this. So it gives an example of the hemoglobin buffer system here. So remember now, when you're making the bicarbonate, you produce a proton. The bicarbonate, of course, gets carried in the blood, but the proton attaches itself to amino acids on the hemoglobin molecule. And it makes the hemoglobin acidic. Yes, it does. But because it holds on to the proton, it reduces the acidity of the blood itself. Because the proton is partially bound to the amino acid, its effects are lessened, right? So hence it has buffered that proton. It's reducing its impact on the blood. All right. Last slide here now is summarizing the buffers, okay? So it mentions here the phosphate buffer system, protein buffer system, and the carbonic acid buffer systems. Please make sure you understand these systems. If there's anything I've said that you're not so sure about, now is a good time. And it's almost 6:30, but anything you're not too sure about, anything you want me to touch on again? Okay. That said, I want to take Friday. Normally we have a class at 11 o'clock on Friday, okay? I want to do an online class on Friday at 11 for the same 1 hour because I want to start digestive system this week, okay? I will post it to Moodle for sure. But if you can make it to that class at 11 o'clock on Friday, it will be online, just like what we're doing here. So I'm hoping to see you all at that time, all right? All right, any questions before we go? I guess I'll let you go.
Sir, this PowerPoint will covers everything that we need to know on this specific topic.
Yes, as I said, we have to use a truncated one because, of course, we're out of time. So we can't mention magnesium and manganese and all the other ones. I haven't
All
even
right.
mentioned chloride ions or anything like that. But I mentioned those when the digestive system still.
Thank you, sir.
All right. Go ahead, Gabriel.
Sir, I had sent you an email. I resent it a while ago, but outside of that email, I sent another one on Moodle. So basically, for the urinary anatomy section, the PowerPoint that's uploaded on Moodle is different from the one that you're discussing in the YouTube video. So which one do we follow, or do we have to do both of them?
And you're doing based on the one that I sent.
Okay. Because there's one in the video and there's one, like a separate, longer one uploaded as a document.
But don't you see the there's no one that is there, the one with the same drawings though? Shouldn't there be one drawing should be external kidney, one
No,
should be
sir, not for the drawing, sir. I'm talking about for the lecture, sir.
oh for the lecture?
Yes. Like you uploaded a video for the lecture and you told us to for urinary system.
Yeah.
And then like the PowerPoint that's there itself is a different one than the one that you're discussing in your YouTube video
Oh, okay, I
or
didn't
in
realize.
the
I will
in video.
check and if it's not there, I'll upload it.
Okay, sir, thanks.
I didn't realize that.
And sir, also, sir, for the lab manual, the lab that you have for the urinary system, sir, it doesn't have the physiology of the lung itself, sir. The external features of the lungs, it only contains the internal features and the the
Said
like
urinary
the
system because a while ago, no, you're talking about lungs.
Sorry, sorry, sir. Oh my God. The kidney.
Right?
Sorry. It doesn't have the big picture of the kidney, the external features of the kidney. It only has the internal structure of the kidney
But
and the
the external one is in the video. The links are
Yeah,
on the
it's in the
slide,
video.
on the
It's from
first
the
slide.
links.
Just check the link. Check the first
Yeah,
link.
it's
Okay.
you're drawing from the videos, not from the PowerPoint.
Okay, sir.
But as I said, I'll check and see. I didn't realize there was a other issue. But as I said, I will be here 11 o'clock on the Friday. Then will be a good time if you want to bring up anything else with regards to the labs. But I do want to start digestive system this week. So ensure that we finish it for next week, right? So remember, if you can, please come 11 a.m. It's going to be just like an hour. So I mean, realistically, it's more like 45 minutes, right? So if you can make it, please come, right? I'll try posting these things on Moodle this week, as probably tomorrow, and then hopefully we can go from there. All right. Remember, I should be seeing you in person next week for your labs. Remember, urinary system is what we are doing for your lab quiz, anatomy and physiology. All right. All right, folks. I will see you all next week, and hopefully I'll see some of you on Friday.
Okay, sir. Bye,
Have a
sir.
good
Sir, remember
rest of your
check
night.
email, please.
Now I'm gonna check it right now, but as I said, for some weird reason, I haven't seen some of the emails just seem to disappear. I don't know why.
Okay, sir.
So I'm gonna check, and I'll try to respond to you like in the next 5 minutes.
Okay, thank you, sir.
Alrighty. All right, guys. See y'all next week.